Part 21. Material Design as Frozen Phi Sentences. The Stuff of Stories. Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We are now in Book 10.4, Reality Engineering. We have surveyed the foundries, the machines that write. Now, we write our first permanent sentence. Not a fleeting wave or a dancing defect, but something that endures. We design and build materials. We step into the materials library, but this is no ordinary library. The shelves are not lined with books, but with samples. A crystal that bends light backward, a foam that completely absorbs sound at a specific note, a lattice as strong as diamond, but light as air. Each sample is not just a substance, it is a frozen phi sentence. Its static geometry is a snapshot of a phase pattern, a story told in atoms or meta-atoms that dictates how waves will move within it. Your new skill is that of the material linguist. You are learning to read the desired function of a material, translate it into a phi pattern, and then freeze that pattern into physical form using our foundries. You are learning to make the stuff of stories. The materials library. The light is soft, indirect. You run your fingers over a sample. It looks like an intricate, microscopic honeycomb carved in silicon. It feels warm, not from temperature, but from the memory of the laser that wrote it. You hold it up. Through it, the room looks wrong. A straight rod appears bent. This is a metamaterial. A material whose properties come not from its chemistry, but from its frozen geometry, its frozen phi. On a nearby table, a hologram displays the relationship. On one side, a desired dispersion relation, a graph showing how fast waves of different frequencies, omega, travel through the material, how they curve and split. On the other side, a proposed unit cell geometry, the repeating Lego block of the metamaterial. An algorithm connects them. This is inverse design. From function, find form. Our puzzle is profound. How do we take a desired wave behavior? I want sound to not pass here. I want light to turn this corner without loss. I want heat to flow only one way. And design a static physical structure whose very shape forces waves to obey that behavior. How do we freeze a verb into a noun? The language role. The translation from function to frozen form. This part teaches a design skill. It is the skill of encoding dynamic wave behavior, a phi clause, into a static spatial structure, a frozen phi pattern. Our core question about phi is, given a target relationship between omega and k, the dispersion relation, that describes a desired wave behavior, what spatial pattern of material density, stiffness, or refractive index, a frozen phi xyz, will force waves to obey that relationship? We are moving from programming waves to architecting the stage upon which they must dance. The anchor image, the organ pipe builder. We will use the anchor image of an organ pipe builder. The organist, the user, wants a specific note, a frequency omega. The pipe builder doesn't just guess a length. They understand the physics of standing waves in air columns. The pipe's geometry, its length, its shape, is the frozen sentence that says to the air, "Thou shalt resonate at 440 Hz. A photonic crystal, or acoustic metamaterial, is like an immensely sophisticated organ pipe, designed not for one note, but for a whole symphony of allowed and forbidden wave behaviors. The builder's craft is knowing how shape dictates sound. The coherent selection principle in material design. In a frozen material, coherence is about long-range order and purity of pattern. Constructive resonance, alignment, in material design means the frozen phi pattern, the geometry, is perfectly periodic or smoothly varying over many, many unit cells. When a wave enters, it meets a coherent, predictable landscape. It resonates cleanly, forming clear band structures and sharp functionalities. Destructive resonance, dissonance, means the pattern is disordered. Fabrication errors, impurities, grain boundaries. These are like typos in the frozen sentence. They scatter waves incoherently, smearing out the sharp functionality, turning a perfect bandgap into a leaky filter. The material designer's mantra is about integrity. If coherence breaks, we stop. If coherence returns, we continue. If our fabrication process introduces too much disorder, too many typos, we scrap the batch. We do not use a material whose frozen sentence is gibberish. Core mechanisms, inverse design and fabrication. We have two main levers: figuring out what shape to make and then making it. Inverse design, from omega k to geometry. This is the heart of the skill. We start with the target property, which is always about how waves behave. Target, a complete bandgap for sound between 1000 and 1100 Hz. This means waves with those frequencies cannot propagate. They are perfectly reflected or absorbed. The phi lens. A bandgap is a constraint clause in the wave's phi field. It says, for this range of omega, there is no possible k that satisfies the wave equation inside this material. The material's geometry creates this clause. The inverse problem. We have software that can simulate waves, solve the wave equation, for a given geometry, and compute its omega k. We run this in reverse. We give the software the desired omega k, the bandgap, and it searches the space of possible geometries for one that produces it. It uses optimization algorithms, often guided by machine learning. It's like the organ pipe builder running a simulation. If I make the pipe this long, what node do I get? But done millions of times to find the perfect shape. 2. Fabrication, freezing the sentence. Once we have a geometry, we must write it into matter using a foundry, 1040. Photonic lithographic foundries. For micron-scale features, for light, microwaves. We use techniques like multiphoton lithography or electron beam lithography. A laser or electron beam draws the pattern in a polymer or resist point by point. It is a direct phi writer. For millimeter to centimeter scale features, for sound vibration. High-resolution 3D printing builds up the complex geometry layer by layer. The freezing process. The crucial point is that we are not assembling atoms randomly. We are imposing a macroscopic phi pattern, the geometry, onto the material. The atoms or meta-atoms are forced into positions that collectively embody the sentence we designed. The coherence criterion, structural coherence over many cells. Our coherence criterion for a successful material is about its frozen pattern. A valid material must have a frozen phi pattern, geometry, that is coherent over many unit cells. This means periodicity. The unit cell repeats with high fidelity. The position of each pillar, hole, or struct varies by less than, say, 1% of the feature size. Low disorder. The number of missing cells, extra cells, or misshapen cells is extremely low. We quantify this as a defect density in the frozen pattern. Smooth interfaces. At the edges of the material, the pattern doesn't end abruptly in a way that creates strong scattering. We might design a tapered transition, an anti-reflection coating made of geometry, to match the wave impedance to free space. If the pattern is incoherent, the material's performance will be degraded, unpredictable, and sample-dependent. It is a broken sentence. The dissonance indicator, brittle design. The primary dissonance indicator is brittleness. A material that exhibits the target property only in a single, perfect, simulated sample, but whose performance collapses with minor real-world imperfections, has a brittle, incoherent design. It is a sentence written in such a convoluted, fragile script that a single smudge renders it unreadable. This often happens with over-optimized inverse designs that find exotic, needle-like geometries in the design space. They work in the perfect vacuum of simulation, but shatter in the rough and tumble of the fab room. A robust, coherent design has tolerance. It has a wide valley in design space. Many similar geometries work almost as well. It can withstand a few typos. The safety rail, tolerance analysis and environmental robustness. Our safety rail is not about immediate danger, but about reliability. A material that fails unpredictably in the field is unsafe. 1. Fabrication tolerance analysis. Before fabrication, we run Monte Carlo simulations. We slightly perturb our perfect design, make holes 2% larger at random, shift struts by 5 microns, and simulate the performance of hundreds of such flawed samples. We compute the statistical distribution of the bandgap center and depth. The design is only approved if, say, 95% of flawed samples still have a bandgap within 5% of the target. This is our tolerance budget. 2. Environmental robustness. The material will be used in the real world. Temperature changes cause expansion. Humidity might swell polymers. Our design must be robust to these parameter shifts. We simulate performance across a range of material properties: Young's modulus, refractive index. The functionality must hold across the expected operational window. The safety rail rule. No material design proceeds to fabrication without passing tolerance and robustness analysis. We will not freeze a sentence that is likely to erase itself. A measurement scene. The acoustic bandgap metamaterial. Let's enact our roadmap's measurement scene. Scene. A 3D printed acoustic metamaterial designed to have a complete bandgap at 1 kHz. The design inverse. We want a material that blocks 1 kHz sound. We run inverse design. The software proposes a geometry, a cubic lattice of complex, twisting plastic shapes, a sonic crystal. Tolerance analysis. Simulation shows the bandgap is robust to plus or minus 3% printing inaccuracy. Fabrication. We print 10 samples using a high-resolution 3D printer, our acoustic foundry. The pass, coherent fabrication. 1. Microscopy. We image the samples. The geometry matches the design. Defect density is low. 2. Measurement. We place a sample between a speaker and a microphone in an anechoic chamber. We sweep frequency from 800 Hz to 1200 Hz. 3. Result. The transmission plot shows a sharp, deep drop, a valley of silence, centered at 1.01 kHz, with a width of 150 Hz. The measured curve overlaps with the simulation prediction within error bars. All 10 samples show nearly identical performance. Pass. We have successfully frozen the sentence, "Thou shalt not pass," 1 kHz sound. The fail, incoherent or brittle. ROPI. Fail A, fabrication disorder. The printer had a clogged nozzle. The samples are full of gaps and blobs. Microscopy shows high disorder. The transmission measurement shows no clear bandgap, just general scattering. The sentence is corrupted. Fail. We must fix the foundry. Fail B, brittle design. The samples look perfect, but the bandgap is centered at 950 Hz, not 1 kHz, and is very narrow. Why? The inverse design found the geometry hypersensitive to the exact plastic density. The real printed plastic has a density 2% different from the simulation assumption. The brittle design collapsed. Fail. We must redo the inverse design with a robustness penalty in the cost function. The prediction spine, the hallmarks of fee-based material design. A mature fee-based design approach yields a clear prediction spine. 1. Predictable performance. A material fabricated to a fee-based design will exhibit the target functional response, for example, negative refraction at a specified frequency, within the statistical variance predicted by the tolerance analysis. Reality will match the error bars of the simulation. 2. Scalable performance. The performance will scale predictably with the number of coherent unit cells. For a bandgap material, the gap depth will increase logarithmically with the number of layers. For a lens, the focus will sharpen with size. This scaling law emerges from the coherent addition of many identical frozen sentences. 3. Phi archaeology of natural materials. When we apply this reading skill backward, we can analyze natural materials. The iridescence of an opal is a frozen phi pattern of silica spheres creating a photonic bandgap. The strength of nacre, mother of pearl, comes from its frozen brick-and-mortar phi pattern of aragonite tablets. Their properties become readable as coherent frozen stories of their formation history. Falsifiability, when the map doesn't match the territory. Our falsifiability threads test the limits of the continuum phi paradigm for matter. If material properties depend critically on atomic scale details not captured by the continuum phi model, for example, the exact electronic orbital configuration of a specific dopant atom, not just its average effect, then the phi approach fails for that class of materials. We would need a quantum phi or a different language altogether for, say, designing high-temperature superconductors. If inverse design, no matter how clever, consistently produces geometries that are unfabricable with any known or foreseeable foundry, geometries with vanishingly thin walls, unsupported overhangs, or atomic scale precision required, then the method is not practical. It is a theoretical curiosity, not an engineering tool. These falsifiers ensure we are building real things, not just beautiful CAD files. Tri-unity in frozen materials. A design material beautifully embodies tri-unity. Time echo dispersion omega k. The target property is defined in the frequency domain, which omegas are allowed or forbidden. This is the material's temporal filter. Space echo frozen geometry. The realized design is a spatial pattern. This is the texture that causes the filtering. Motion echo wave propagation. The combination dictates the motion of waves within the material, whether they propagate, are reflected, or are localized. This is the emergent dynamic behavior. Designing a material means carefully crafting the space echo geometry to control the time echo dispersion and thereby govern the motion echo wave behavior. Lanterns across scales, the grammar of stuff. This principle of frozen phi governs structure and function at many scales. Near scale, photonic integrated circuits. We design waveguide bands and splitters on a silicon chip. The frozen sentence is the etched pattern of silicon that guides light. A perfectly coherent band has near zero loss. A disordered etch scatters light, hitting the chip. Middle scale, architectural acoustics. The shape of a concert hall, its walls, ceilings, diffusers, is a frozen acoustic phi pattern. A well-designed hall has geometry that creates coherent, pleasing reverberation, constructive resonance, for the audience. A bad hall creates echoes and dead spots, dissonance. Far scale, geological formations. A mountain range can act as a frozen phi pattern for weather systems, channeling winds and creating rain shadows. The Grand Canyon is a frozen sentence written by water in rock, and it now governs the flow of air and sound within it. This is passive, natural material design on a planetary scale. The ethics of frozen sentences. The responsibility of lasting imprint. The ethics of material design is the ethics of creating lasting, functional artifacts. 1. Containment through degradability. Some materials, especially novel metamaterials, might have unforeseen environmental interactions. The ethical design includes a planned degradation clause, or end-of-life recyclability, designed into the phi pattern itself, for example, using biopolymers that dissolve or geometries that easily separate. 2. Transparency of function. A invisibility cloak metamaterial could be used for surveillance or warfare. The ethical burden is on the designer and fabricator to consider the context of use. This begins the conversation that leads to Book 10.8's stewardship institutions. 3. Auditability of provenance. Each material sample should carry a digital twin certificate, a hash linked to the exact design file, fabrication logs, and tolerance test results. This creates accountability. If a beam collapses, was it a design flaw, a fabrication error, or misuse? The frozen sentence comes with its provenance. Power to create new matter brings the duty to ensure that matter is sound, safe, and its story is known. The recognition skill, seeing the frozen verb. You know you need this skill when you see a natural or artificial structure and intuitively connect its shape to a function. The flutes on a classical column are not just decoration, they are a frozen pattern for scattering light and creating a sense of rhythm. The dimples on a golf ball reduce drag, a frozen aerodynamic phi pattern. The fractal branching of a lung or a river basin is a frozen pattern for optimizing flow and surface area. The moment you look at a shape and ask, what wave, what flow, what force does this geometry orchestrate? You're thinking like a material linguist. You're seeing the frozen verb in the static noun. The master tree location. This part, 10.4.1, is a core pillar of Book 10.4. It depends on 10.1.2, clause library, for understanding dispersion relations as constraints, and on 10.4.0, foundries, for the physical means of fabrication. It is the first practical application of reality engineering. It enables the next steps. Field engineering, 10.4.2, where we sculpt dynamic phi fields within such materials, and patch creation, 10.4.4, where we assemble materials and fields into localized regions with custom laws. This is engineering the stage, upon which the dynamic drama of waves will play. Return to the phi. Let us zoom out. A material is a region of space where the phi field has been pinned into a specific persistent pattern. In a crystal, atoms are pinned in a lattice. This frozen phi pattern of nuclear positions dictates the electronic band structure, the omega k for electrons. In a metamaterial, we pin larger scale features to dictate omega k for light or sound. We are not creating new physics. We are creating new, coherent boundary conditions that shape how the universal phi field expresses itself in that region. We are writing local, permanent grammar rules into the fabric of space. Zenodo and the equations of frozen light. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. The papers detail the inverse design algorithms, topology optimization, adjoint methods, the rigorous treatment of dispersion relations in periodic media, Bloch's theorem, the statistical mechanics of fabrication disorder, and the experimental demonstrations of phi design metamaterials for cloaking, lensing, and vibration isolation. They provide the mathematical and experimental proof that matter can indeed be programmed like a sentence. So, picture yourself back in the materials library. You pick up the silicon honeycomb. You now see it not as a curious trinket, but as a manifesto. It is a physical argument about how light must behave. You designed it. You specified the forbidden frequency. You ran the inverse solver. You tolerated its quirks. You sent the file to the lithography foundry. And here it is, in your hand, bending light to your will. You have just learned to write matter. You have frozen a phi sentence into a thing you can hold. This is part 10.4.1. Material design as frozen phi sentences, the stuff of stories. It is the first tangible fruit of book 10.4. In our next session, we will bring the stage to life. Having built the static set, we will learn to direct the actors. We move to field engineering, 10.4.2. We will learn to use our foundries not to freeze patterns, but to sculpt dynamic flowing phi fields in real time, to create stable vortices, guiding channels, and dynamic lenses within the materials we've just designed. We will learn to make the stage itself dance. Remember, one field phi with its infinite echoes. We have learned to freeze one echo into permanent form. Now we learn to conduct the living symphony within it. Salam, and peace be upon you.